In this training, learn how to build the Infineon F-MAC Wi-Fi driver as a standalone module on an NXP Linux BSP. The focus is on a practical and flexible workflow. This approach avoids rebuilding a full Yocto image and speeds up development and testing. This training is designed for i.MX Linux developers working with Murata Wi-Fi and Bluetooth modules. These modules may use either SDIO or PCIe interfaces. We will build the FMAC driver out of tree directly against the NXP Linux kernel. This method works across multiple Murata modules and does not require a full Yocto rebuild. In this step, we prepare the cross-compilation toolchain required to build the kernel and the FMAC driver. We begin by setting up the NXP i.MX Yocto project Linux BSP layers. A new working directory is created, and the NXP manifest repository is initialized using the appropriate branch and manifest file for the target BSP release. After initialization, the repositories are synchronized to download all required layers. Once the sources are available, we start the Yocto build environment for the target machine. At this point, the license agreement must be reviewed and accepted before continuing. Instead of building a full image, we build only the cross-compiler by running the meta toolchain target. This generates a standalone cross-compiler matching the NXP kernel and BSP. After the build completes, the cross-compiler installer is located in the deploy directory. The installer is made executable and run on the host system. This installs the cross-compiler and environment setup scripts. These tools will be used later to build both the kernel and the FMAC driver. If a compatible toolchain is already installed on the system, this entire step can be skipped. Before going into individual commands, let's understand the complete flow of the process. We start by preparing the NXP kernel source and configuration so it matches the BSP running on the target. Next, we obtain the Infineon F-MAC Kraken package and generate a backports configuration that aligns with the kernel. Once the configuration is ready, the FMAC driver modules are built against the prepared kernel source. After the driver build, the required firmware, regulatory files, and NVRAM configuration are added. If needed, the device tree is updated to describe the Wi-Fi hardware correctly. Finally, the modules are loaded on the target system and validated. In this step, we prepare the kernel source that FMAC will be built against. We begin by cloning the official NXP Linux kernel repository. It is important to check out the exact kernel version used by the BSP to ensure binary compatibility. Once the correct branch is checked out, we source the environment setup script provided by the cross-compiler. This configures the cross-compiler and target sysroot. After the environment is ready, we select a default kernel configuration that matches the target i.MX platform. At the end of this step, the kernel source tree is ready for configuration and build. Now we adjust the kernel configuration to make it compatible with FMAC. First, the wireless configuration is modified so that CFG 802.11 is built as a loadable module. This is required because FMAC provides its own backported wireless stack. Next, regulatory database signature checks are disabled to avoid conflicts with FMAC's regulatory handling. Additional cryptographic options are then enabled so the kernel can parse and validate regulatory data correctly. Once all configuration changes are applied, the kernel configuration is updated and the kernel image is built. This build step ensures the kernel headers and symbols are ready for the FMAC driver build that follows. In this step, we download the Infineon F-MAC driver package, specifically the Kraken release. This package includes a backports framework that allows newer Wi-Fi drivers to run on the selected kernel version. After downloading the archive, it is extracted to access the backport source tree. Inside this directory, you will find the FMAC driver, wireless stack components, and build infrastructure. This source tree will be used in the next step to configure and compile the driver. The FMAC build is performed in two distinct phases. In the first phase, we generate the backports configuration and build the required host tools. This step is intentionally done without sourcing the Yocto toolchain to avoid conflicts with host utilities. Once the configuration is generated, a new terminal session is used. In this second phase, the Yocto cross-compiler environment is sourced. The FMAC driver and related kernel modules are then cross-compiled against the prepared NXP kernel source. At the end of this step, the FMAC driver module and supporting wireless modules are ready for deployment. The FMAC driver requires additional runtime files to operate correctly. These include the firmware binary, a CLM regulatory blob, and an NVRAM configuration file. Each file is specific to the Murata module and chipset being used. They are downloaded from Infineon and Murata's public GitHub repositories. The NVRAM file must be renamed following the expected naming convention so the driver can locate it at runtime. Once these files are in place, the driver has all the required runtime dependencies. In some cases, the device tree must be updated to correctly describe the Wi-Fi hardware. Murata provides ready-to-use device tree patches for common NXP evaluation boards. The appropriate patch is copied into the kernel source tree and applied. This updates SDIO or PCIe nodes, GPIO assignments, and power sequencing information. After applying the patch, the device tree blobs are rebuilt. Device trees with M2 or M200B suffixes are intended for Murata adapter boards and should be selected accordingly. FMAC requires additional support in user space Wi-Fi tools. For this reason, host APD and WPA supplicant must be patched with Infineon-provided changes. We begin by cloning the upstream host AP repository and checking out a known compatible revision. Next, the Infineon patch archive included with the FMAC release is extracted. Each patch is then applied sequentially to the host AP source tree. This ensures proper interaction between the FMAC driver and user space Wi-Fi management components. After patching, host APD is configured and built first. The default configuration is copied and updated to enable required features such as WPA3 if needed. The build process produces the access point binaries. Next, the same process is repeated for WPA supplicant. This generates the client-side Wi-Fi management binaries. Once built, all binaries are ready to be deployed to the target system alongside the FMAC driver. You have now completed the standalone build of the Infineon F-MAC driver on an NXP Linux BSP. This approach avoids rebuilding a full Yocto image while supporting Murata SDIO and PCIe modules. We walked through kernel preparation, FMAC backports configuration, driver compilation, firmware setup, optional device tree updates, and user space tools. This workflow enables faster debugging, validation, and iteration during Wi-Fi bring-up.